Okay, good. Right, so we're now going to try to do this Jupyter notebook. Okay, so if you go to a web browser and type that, which I will copy and paste into the Feishu group here. Right, yeah, if you go to that, in a web browser, you should be able to log in with the username and password that I sent to you. Okay, so basically, go to the web browser, type the address, type your username, and type your password, log in, and it should start a server for you. Okay. All right. Just check everybody's logged in. You can log in. Oh, you can use PuTTY if you want. It's just if you use so you've logged in on PuTTY. That's fine. Does it work? I use PuTTY. Okay. Right. So. Right. So what I want to do is basically encapsulated within a document that I thought I sent earlier today, but doesn't seem to be in the group. Seem to be having some problems with sending things. Let me just make sure about that. Oh no, okay. Right. So what I've sent is how to log on to the teaching computer in PuTTY or in SSH, but there is also the option of logging in with the Jupyter Notebook and do some scripts in Python. Okay, now, problem is I haven't managed to send you the second document, so let me try to fix that. Just a moment. Just a moment. This is very slow today. Right. Seems to be working now. Okay. So this is the second document that I've prepared for you. So basically, it tells you how to log on to a Jupyter Notebook, but more importantly, how we're going to format these calculations in a way which is kind of general and is not doesn't teach you how to use one piece of software, right? Because what we have to remember is plane wave DFT is not just one piece of software, right? There's CastStep, which is the software that I've worked on for a long time. There's VASP. There's Quantum Espresso, Abinit, all kinds of plane wave programs. And if you have a research career, or even if you go into a company and do research in a company, and you're doing DFT in a company, whatever, if you're doing DFT, when you move from place to place, different groups and different institutions use different software. Okay, so learning one piece of software is not the best approach, in my opinion, because when you go to the next place, then you need to learn a new piece of software. Okay, what's better is to learn the fundamentals. What's better is to learn the mathematics and how it works internally, and then to use a kind of wrapper around the software, and then you can use any piece of software. Okay, so the wrapper that we're going to be looking at today is called ASE, the Atomic Simulation Environment, and in ASE you can ask ASE to run a calculation in, for example, CASTEP or VAS, Quantum Espresso, or even other pieces of software which are not plane wave software like Gaussian, NWChem, Yamba, lamps. You can do whatever you want. Okay, so let's try to go a bit quicker. So what I'm going to do here is I'm going to close some of this stuff. Let's close some of this stuff. Get this out of the way. Right. And I think I'm going to make a new directory here. Okay, so I'm going to make a new directory, and I'm going to call that this. Right. So basically, what I'm doing here is I'm making a new Jupyter notebook. Okay, and I'm going to call this class 1. And in here, I'm going to write a script that is going to make some input files for a plane wave DFT calculation. Okay? So the way I'm going to do that is I'm going to use ASE. So the first thing to bear in mind is ASE has an online manual. Okay? So if I go Atomic Simulation Environment, and we go to the online manual here, it's useful to have this open, and you can see this is the software that ASE supports. So I can run calculation, or I can set up calculations in ASE, and I can ask ASE to produce an input file which is compatible with CASTEP, or is compatible with VASP, or Orca, or Gaussian, or GPOR, or any of the software, right? Okay, so what I'm going to do here is I'm going to use ASE to make an input file. So the first thing I'm going to do is all in Python, all right? First thing I'm going to do here is I'm going to set up a crystal, okay? So I'm going to say from ASE, what? From, is it working? Is it working? Is yours working? So this is the problem I had earlier. I'm wondering whether there's a problem with the server. Is yours working? Is it working? Not working. Yeah, this is the problem I had earlier. So it seems to be having some issues, some problems. So I think I need to go to the office and restart the computer. Yeah. Sure, but that means that you can't also run it. Okay, so I'll run it on this computer, locally on this computer, and I'll try to fix the server today, and then you can log in and try it yourself later, okay? Because unfortunately, it seems to be having some problems. Okay, right. So I'll start a Jupyter on my computer, and let's. Okay, this is. I'll do one here. I keep pressing the wrong button. Right. So what I'm going to do is to start a Jupyter notebook, and I'm going to call this class 1. Okay. What I'm going to do is I'm going to say from ASE dot build import bulk. Right. So bulk means a bulk crystal. Okay. So for example, we could do a metal FCC crystal, transition metal FCC crystal. So does anybody have any suggestions? What's your favorite metal? Silicon. We can do silicon. But what about a transition metal? Palladium? Palladium. Okay. So let's do PD equals bulk. We'll do silicon next, right? But doing a metal is a bit easier first. Okay. So what I'm going to do is I'm going to say I'm going to make palladium. Okay. And then if I run that in memory, I now have palladium in memory. If I look in memory, I can see I've got some atoms here, palladium atoms in a cell. Okay. I want to view that. I want to see it. So in ASE, what I can do is I can say from ASE.visualize import view, and I can view PD using viewer equals ngl, right? And we can have a look at that. Apparently, I don't have the extension on my laptop. So I tested this on the computer, on the server computer. I didn't test it on my laptop, so apparently I don't have the what I need installed on this laptop. That's unfortunate. All right, let's see if we can fix this problem. All right. And everything's very slow. Okay, is it working? Okay, let's try that. It's just not, it's just refusing to work today. I don't know what's the problem. Can't enter any directories. Huh? Huh?
You have problems with the web service.
Yeah, it just seems like everything is having a problem today. I don't know exactly what's going on.
You need to connect to the internet to use this service.
Huh?
The collab.
But is it working for you? Yes. No.
I have a good region and maybe will help you.
Oh, but the server is on campus, so it requires no VPN. The problem is that the server is not working. The server needs to be restarted. I don't know. I don't know why. Just a moment. All right, let's try again. Hopefully it works eventually. Right, so I'll try this again. No module named ngl view. So according to this, I do have ngl installed, but all right. So I'm going to have to try. You know, it may be quicker for me just to go back to the office, restart the computer, and come back again. If I take a bike, I could probably be back in 10 minutes. Yeah, I think I'm going to do that. So I'm just going to run over to the chemistry department, restart the computer, come back, and then I think things will be okay. Okay? I just need to restart that computer. Okay? Sorry? Yeah, but I think if I just take a bike and come back again, it would be quicker if I just go on my own and then come back. I think I can be back in 10 minutes. Okay? Sorry about that. Yeah, completely forgot about this. Every month on the first of every month, so it's the second today, so yesterday, they make me log into the computer, and this is what happens. Right. Okay. So I guess the first thing we can do, first thing we ought to do, is re-enter that text. Good. So now we can view it, and we can see our palladium cell. Okay. So what you'll notice is that this does not look a lot like FCC palladium, right? And this is because what we're looking at here is the primitive cell of palladium. Okay, the primitive cell. So we talked yesterday about cells, conventional cell, primitive cell. Primitive cell is the minimum volume, minimum number of atoms that we need in order to represent a crystal lattice. So this is FCC palladium, but it is the primitive, not the conventional cell. If we want the primitive cell, if we want the conventional cell, we can say we want a cubic, right? Cubic or orthogonal, I think it is, true. And now what we see is the conventional cell, which looks a lot more like with what we're familiar with of FCC crystals. Okay, so we've got an atom on the vertex, and then an atom on the front, side, and bottom face. Okay, so we've got FCC palladium. What we want to do with this crystal is to do a calculation, a DFT calculation of palladium. Okay, so with ASE, what we need to do is we need to load what's called a calculator. Okay, so in ASE language, a calculator is the interface between a DFT package like CASTEP or VASP and the ASE Python environment. Okay, so what I'm going to do is use the CASTEP environment, the CASTEP calculator, and to use that, I'm going to import it. So I'm going to say from ASE.calculators.CASTEP import CASTEP, right? So this puts the CastStep Python environment into memory. And so now I can use that environment in this cell of my Jupyter notebook. Okay, so what I'm going to do is I'm going to make a calculator. I'm going to call it calc. And I'm going to set it equal to CastStep, right? If I do that and run it, I now have calc in memory. I can interrogate that memory and look at it, and it tells me that these are the keys that it's going to pass to CastStep, and it says it has no atoms and it has no cell. Okay, so what we need to do is connect this cell we made, the palladium, to the CastStep calculator, right? So in order to do that, all I need to do is I need to say calc. I need to say palladium.calc, so the calculator of palladium equals the calculator that I've just set, right? If I do that and now interrogate the calculator, we can see now our calculator has the 4 palladium atoms and the cell of the FCC palladium that we just made, okay? So the next thing to do is to ask, okay, so I've made this calculation, this very basic calculation, how can I run it, okay? The way I'm going to run it is I'm going to ask the calculator to make some input files for me, right? So I'm going to say calc.prepare input files, okay? And if I do that, what you notice is there's a new directory here, CastStep, with 2 input files, which I can run in CastStep, okay? So now I can run this calculation in CastStep, right? And in order to do that, if you're in PuTTY, what you would do is you would have a terminal. It would go to the directory, okay? And you would want to run CastStep. So on this server, what I have is the software installed into environment modules. Okay, so if you type in module avail or module available, it tells you what modules are available. So on this system, what we have is CastStep, Quantum Espresso, VASP, and Gaussian. Okay? So because this is my code, CastStep, I'm going to use that. So what I'm going to do is I'm going to say module load compchem/CastStep. Okay? So now CastStep is in the path. So if I do cast and press tab on the tab button on the keyboard, you see it auto completes because CastStep is now in the path. Okay? So that's CastStep, right? And if I want to run this calculation, well, this calculation is called CastStep, right? So I'm going to run CastStep, run it, and what you'll see, if I refresh, is now we have a CastStep.CastStep output file, okay? So a couple of seconds, we've got a pseudo potential, okay, a palladium pseudo potential, LDA. And we just wait a few more seconds and see what happens. We can have a look at the input file as well. Right, so we can see that it's doing something in here. It's a little bit slow, but it's doing something. Right. So when we say CastStep, what we're saying is basically do my calculation for me, start the calculation. Okay. I was expecting it would be finished by now. Okay. So we can have a look at the output, and we can see what's actually happening here. So what we can see is we have this table of the SCF loop. So if you remember from earlier, this thing, when we were looking at this this kind of flow chart, the DFT flow chart, and we said we need to go on a loop around like this, right, like that. What we're doing in CastStep right now is we're going around this SCF loop. Okay, so we're going around and around and around, and what we see in here in this, it's finished. Good. Right, so what we see in this table is that SCF loop. So in total, we did 14 iterations, and every time we got an energy, okay? And once the energy was not changing anymore, so this is how much the energy is changing, right? Then we stop, and we get the final ground state energy, right? Okay, so you can see it's quite easy to do a calculation in this way. The advantage of using ASE is I can make my palladium system, my crystal, or any crystal, and I can choose a different calculator. So I could choose not to use CASTEP and instead to use Quantum Espresso or VASP, right? All that I need to change in order to change from CASTEP to VASP or CASTEP to Quantum Espresso is this calculator, okay? Right, so now I want to make this calculation more, I want to make it more elegant, okay? So at the moment, my calculation is called CASTEP, right? It's a CASTEP calculation called CASTEP, and all of the input files are called CASTEP, right? If I have to do, I don't know, 100 calculations on palladium, platinum, silicon, you know, all kinds of different things, if they're all called CASTEP, I'm going to get confused very quickly, okay? So I need to make this a little more elegant. Okay, so what I'm going to do is I'm going to take my palladium and I'm going to write, so I'm going to write some markdown, and I'm going to say, make it more sensible, right? Make it more sensible. So I'm going to have my palladium, so I make it the same way. I'm going to make a CASTEP calculator, right? But this time, what I'm going to do is I'm going to give it a name, okay? So I'm going to give it a name, and my name is going to be, I don't know, PD, right? This is my name. And so in CASTEP, what I'm going to do is I'm going to say that my label is going to be name, and my directory is going to be name, okay? And this is going to keep everything in a kind of file system which is easy to keep track of, okay? And so I'm going to take my palladium calc, and I'm going to set the calculator equal to the calculator I've just created. And now, last time what I did was I made an input file, okay? Prepare input files. This time I'm going to run the calculation directly within the Jupyter Notebook. So I'm going to say energy equals, and I'm going to set calc dot, or even, well, what do I want? Potential energy. All right. Potential energy. Or is it get potential energy? Get potential. Right. Okay. So what I want to do is I want to ask CASTEP to run the calculation. The problem is when I'm running in Jupyter Notebooks, at the moment it does not know how to run CASTEP, right? So I need to tell it the path to run CASTEP. So what I'm going to do is I'm also going to say command equals, and the way we ran it last time was castep.mpi, right? Right. But I can also tell it to run more than one process, so it's a bit faster. So last time we ran on one processor, I can run on 2 or 4. So I'm going to say mpi run minus np 4 processors, run CASTEP like that, right? So how do I know how to do this? I mean, I should probably mention that. So this is the manual for ASE. So if you go into modules, it has all of the information you need on setting up calculations. So if I go to calculators and I find CASTEP, right, it tells you all of the things I've just said, right? So for instance, right now I'm going to set up a CASTEP command, right? And I'm going to do it if you didn't know how to do that already, you could go to the ASE directory and you could read about, okay, I need to change the castep command. How do I do that? Here's the manual. It tells you how to do it. Okay. So the point is, you don't need me to tell you how to do it. You've got the manual. You can find out how to do it very easily. Okay. You just read about it. So I'm going to set castep command. Command. Right. I'm going to run it again. Okay. So now MPI cannot find the path to castep, right? And the reason for that is, if you remember, when we did when we ran castep ourselves, we had to module load compchem castep, right? So I've also set up on this computational server, I've also set up a system to load environment variables within the Jupyter Notebook, right? So what we can do is we can do module, right? And we can do load, and we can do compchem / castep, like that, and that will load the castep environment within the Jupyter Notebook so that we can run it, okay? So we can do that in here just like that, okay? And so now, after doing all of those steps, what we have is a fully enclosed calculation in a Jupyter Notebook, running in castep, running in parallel, running a simple LDA calculation of palladium, okay? So what you can see is, all we have to do is those lines, and we have a DFT calculation running straight away, okay? So it has the name PD, because we set the name to be PD. We go into PD, we can see that our calculation is running in here. We go through, we can see that it converged 14 iterations again, and it's finished. We can see we've got a warning here. You can see that we've got a warning here, which we can worry about later, right? But right now, we want to check that we've got an energy, okay? So if I just ask what the energy is, okay, we can see in EV, our energy is minus 13,978 EV, okay? Right, now, I don't know what to do now because it's break time, but because everything went wrong, I think we're quite far behind, so maybe I should just keep going. Although maybe it's a good idea to have a break. I'll tell you what we'll do. We'll have a short break, okay? So if anyone needs to have something to drink or go to the bathroom, we'll take a break for, say, 3 minutes, right? We'll come back at 11, okay? Let's have a short break, and then we'll continue. A 3-minute break.